By the end of this module, you will have a basic understanding on cooling tower fan system, how it works traditionally, and Danfoss solution. The key benefits of using a VLT HVAC drive with cooling tower systems. Let's start with the cooling tower fan module. Let me introduce you to the module with a description of the cooling tower application. Cooling towers are used to cool warm condenser water in water-cooled chiller systems. The warm water absorbs heat from the chiller's condenser section and releases it into the atmosphere in the cooling tower. The tower fans provide moving air to cool the warm water, primarily by evaporation. The concept is to return a constant condenser water temperature to the chiller. Let me explain the construction of the cooling tower to you. The 3-cell cooling tower shown has axial fans mounted on top of the tower. These fans draw cooling air through the sides of the tower and exhaust it through the top of the tower. The shafts of the motors are horizontal, while the fan shafts are vertical. A right-angle gearbox is mounted at the base of each fan, and a long drive shaft connects the drive motor to the gearbox. Now that you have seen the construction, let us see how the cooling actually takes place. The warm water is sent through a water inlet pipe to the cooling tower. Then, it is distributed across the top of the cooling tower, and gravity causes the water to cascade down the sides, across film material. The film material causes the water drops to break into smaller water droplets, creating a larger surface area for heat transfer. The cooling tower fans draw air across the water droplets, cooling by an exchange of latent heat, resulting from evaporation of a small amount of water. After passing through the cooling tower, the water collects in the tower basin, and is pumped back to the chiller condenser section by the condenser water pump. In cold weather operation, the cooling tower will have a heater in the tower basin to keep the water from freezing. These cooling tower installations are commonly found in large air conditioning systems for facilities such as airports, university campuses, hospitals, office towers, and hotels. Cooling tower fans need to be controlled because cooling towers are designed for maximum load conditions. However, in most of the applications, maximum load occurs for only less than 10% of the time. Therefore, if controlling flow becomes important, the speed of the motor driving the cooling tower fan can be controlled. This control saves energy, reduces wear and tear, reduces audible noise, reduces water use. Let us see how this control system works. We shall first start with the traditional system. In the traditional method, energy conservation is accomplished through different control methods. They are using on-off control, or 2-speed motors, using adjustable pitch blade fans, modulating discharge dampers for centrifugal fans. I shall further explain each of them. Let us consider the simplest method of capacity control, on-off control, or fan cycling. The HVAC system load on the chiller, and the outside wet bulb temperature, determine the operation profile of the cooling tower. As the wet bulb temperature, or HVAC system load varies, the required airflow through the cooling tower also varies. On-off is an inexpensive method of capacity control. However, the motor may burn out from too frequent cycling problem. That is why wide temperature bands are established, that is, when the temperature exceeds the higher limit, the fan is staged on. And then, the fan is staged off, upon reaching the low temperature limit. On and off control can be used with one shell or tower, or with multiple shells, and is the most common form of cooling tower fan control. It provides moderate savings at low cost. Maintenance cost for on-off control is high. However, cycling the fan on-off places mechanical stress on the components, such as the motor shaft and couplings. Also, the motor burnout from too frequent cycling is a concern. Two-speed fan motors are commonly used on the cooling towers to provide two-speed, instead of single-speed, control of fans. Even though they are costly, they have the advantage of providing reduced energy consumption and reduced cooling tower load. The building's air conditioning load and the outside air wet bulb temperature determine the size and operation of a cooling tower. Let us now see the control using adjustable pitch blade fans. These fans offer more precise temperature control. But the mechanism to regulate the blades can be expensive and is often such a maintenance burden that they often cease in position, causing the fan to operate as a fixed blade fan. We find that in the traditional method, though there is an attempt to save energy, maintenance is a big burden. Can we overcome this maintenance problem and make operation more efficient? Yes, we can, by using the Danfoss VLT HVAC drive. Remember, we said earlier that the concept is to return a constant condenser water temperature to the chiller. The warm water enters the cooling towers through the inlet at the top of the tower and is sprayed directly or distributed and cascades through the fill. The cooling tower fans draw air through the tower to cool the water. Using the VLT HVAC drive, the cooling tower fans can be controlled in direct response to the condenser return water temperature. The VLT HVAC drive controls the fan speed by utilizing a temperature sensor in the cooling tower basin or return water piping. If the basin water temperature starts to increase, the VLT HVAC drive increases fan speed to provide additional cooling of the water. If the water temperature is less than the set point, the VLT HVAC drive slows down the speed of the fan. Since the power required for a cooling tower fan varies by the cube of its speed, a small reduction in speed produces significant energy savings. The VLT HVAC drive can extend the life of the fan drive assembly, that is gearboxes and belts with infinite speed adjustment, compared to fan cycling. We just saw that Danfoss VLT HVAC drive provides energy savings in the application. To calculate the potential savings over time, the actual load versus time profile must be known. The load profile indicates the amount of flow that the system requires to satisfy its load during a typical day, month, year, or the time period under study. Take a look at the graphic. It shows a typical load profile for the HVAC system. The cooling tower will reject heat most of the time, even when the HVAC system is on cooling and operating less than full capacity. A VLT HVAC drive will reduce the cooling tower fan speed to match this capacity. A small reduction in speed saves a large amount of energy because of affinity laws. This profile will vary depending on the specific needs of the system due to temperature and relative humidity, geographic location, requirements from authorities, safety margin used in the design phase, and several other factors. The energy consumption graphic shows how very little energy savings is available with on or off controlling of the cooling tower fan motor, while the VLT HVAC drive saves energy by reducing the motor speed. Apart from the advantages of energy savings and easy maintenance, there are some key features that improve the performance of this application. Let us see these key benefits, one by one. As the speed of the cooling tower fan is reduced beyond a certain level, the fan's cooling efficiency becomes insignificant. Also, when a cooling tower utilizes a gearbox, a minimum speed of 30% is required for proper lubrication. The programmable minimum frequency setting of the VLT-HVAC drive provides the ability to maintain a minimum frequency, that is a minimum speed of 30% even if the feedback, or speed reference, calls for lower speeds. This ensures minimum fan speed operation for adequate lubrication for the tower fan gearbox. Next comes the sleep mode feature. The VLT-HVAC drive can cycle the fan on and off by utilizing the sleep mode feature. When the cooling tower basin water temperature is at set point for a predetermined amount of time, the VLT-HVAC drive automatically stops the fan. When the temperature increases, the VLT-HVAC drive restarts the motor to maintain the set point temperature. This minimizes fan motor operating hours and increases savings. Another important feature is frequency bypass. Some cooling tower fans have undesirable resonant frequencies that can cause mechanical vibrations in the tower. This could possibly damage the mechanical components. These frequencies can be avoided with the VLT-HVAC drive by programming up to 4 bypass frequency ranges. This allows the fan motor to step over those speeds, which induce resonance, thus providing vibration-free operation. The next feature is the motor preheat. When the motor is stopped, the VLT-HVAC drive can apply a small DC current into the motor continuously to keep the wiring dry and protect it from condensation. The motor preheat feature can extend a motor's operational life. Another feature is that of de-icing. For towers that use an axial fan, the VLT-HVAC drive has the capability to de-ice the tower by reversing the airflow. In this process, the air passes over the warmer water in the basin and exhausts it through the fill-in tower inlets, thus melting the ice accumulation. Reversing the fan and running it at a reduced speed can be controlled by the VLT-HVAC drive. Before ending this module, let me give you a brief summary of what we saw. As we saw that, in the traditional method, energy conservation accomplished through on-off control has an advantage of low cost, but it has a problem when the motor is burned out from too frequent cycling. In control, using continuously adjustable pitch fan blades, even though these fans offer more precise temperature control, they have the disadvantage in the mechanism to regulate the blades, which are expensive, and is often such a maintenance burden. Thus we find that, in the traditional methods, though there is an attempt to save energy, maintenance is a big burden. You will find that in the Danfoss solution, where a VLT-HVAC drive is used, there is considerable energy savings when compared to the traditional methods. A study of the energy savings shows that very little energy saving is available with on and off controlling of the cooling tower fan motor, while the VLT-HVAC drive saves energy by adjusting the motor's speed. With this, we come to the end of this module, describing the cooling tower application.